Welcome friends, Igor is here, and in this video we will talk about isomorphism of vector spaces. In this lesson we will define what it means for two vector spaces to be isomorphic, construct an example of two isomorphic vector spaces, and we will prove that isomorphic vector spaces must have the same dimension. Let's get started. Let's go back to the roots of vector spaces. A vector space is a set of objects which we call vectors, which is endowed with two operations, vector addition and scalar multiplication. These operations must satisfy a list of 10 specific properties, and these operations put some kind of structure on the vector space. But we can also transfer this structure from one vector space to another vector space via linear transformations, because they respect the operations of vector addition and scalar multiplication. But when we have an invertible linear transformation from one vector space to another vector space, then we can not only translate questions about spans, linear independence, basis, and so on from the first vector space to the second vector space, but also we can use the inverse of the linear transformation to translate these same questions from the second vector space back to the first vector space. So the structure of the first vector space can be transferred to the structure of the second vector space, and the structure of the second vector space can be transferred to the structure of the first vector space. So in essence, these vector spaces have the same structure, and these invertible linear transformations realize the transfer of this structure. We are interested in the underlying structure of the vector space rather than what it looks like. From this point of view, if there is an invertible linear transformation between the two vector spaces, then these vector spaces are structurally identical. In mathematics, this phenomenon is usually encoded by the word isomorphism. Two vector spaces U and V are isomorphic if there exists an invertible linear transformation T from the vector space U to the vector space V. This invertible linear transformation is called an isomorphism between the vector spaces U and V. These terms originate from Greek, and to be isomorphic in Greek means to have the same form. Iso, same, morph, form. It is a simple but interesting and instructive exercise to make sure that the relation of isomorphism is an equivalence relation on the set of all vector spaces. Here is an example of two isomorphic vector spaces. We have this linear transformation T that goes from the vector space of polynomials of degree at most 3 into the vector space of matrices of size 2 by 2. In a previous video we saw that this linear transformation is invertible, and the inverse linear transformation S from the vector space of matrices to the vector space of polynomials is given by this formula. This means that the vector spaces of polynomials of degree at most 3 and 2 by 2 matrices are isomorphic. In other words, they have an identical structure as vector spaces. Here is an intuitional way of looking at this notion of isomorphism and having identical structure. What does a typical element of the vector space P3 look like? It is a polynomial of degree at most 3, and it is described by 4 coefficients A, B, C, and D. A typical element of the vector space of 2 by 2 matrices is a matrix of size 2 by 2. Such a matrix is characterized by its 4 entries A, B, C, and D. Do you see the similarity between these two types of objects now? Both of them are defined by a list of 4 numbers. They simply represent the same structure in different ways. In the vector space P3, we take these 4 numbers and use them as coefficients in the monomials, whereas in the vector space of the matrices, we take these 4 numbers and put them into a square array of size 2 by 2. So this is nothing but 2 different ways of looking at the same objects. If two vector spaces have the same structure, then they need to have identical characteristics, and one of the main characteristics of a vector space is its dimension. So it is only natural that if two vector spaces are isomorphic, then they have the same dimension. Let's assume that the vector spaces U and V are isomorphic. This means there exists an invertible linear transformation T from the vector space U to the vector space V. In a previous video, we proved that to be invertible for a linear transformation is the same as to be injective and surjective. In particular, this linear transformation T is injective, and in the video on the properties of injective linear transformations, we proved that an injective linear transformation cannot go from a higher dimensional vector space to a lower dimensional vector space. This means that the dimension of U cannot exceed the dimension of V. But also T is surjective, and in the video on the properties of surjective transformations, we proved that a surjective linear transformation cannot go from a lower dimensional vector space to a higher dimensional vector space. This means the dimension of U must be greater than or equal to dimension of V. But T, as an invertible linear transformation, must be both injective and surjective. So both of these inequalities must hold. But if they both hold, it means dimension of U is equal to the dimension of V. And this is exactly what we were trying to prove. A remarkable fact that we are going to prove very soon is that this also works in the opposite direction. Namely, if two vector spaces have the same dimension, then in fact they are automatically isomorphic. So you'd better stay tuned for the upcoming videos because you don't want to miss this one. If you found this video useful, please give it a like to help others discover this content, and subscribe to this channel to see more of these videos. In the next video in this series, we will figure out how to compute the inverse of an invertible linear transformation. I will see you later.